Hello everyone, my name is Neiheiser and I'm going to present you our work, Kauri, Scalable BFT Consensus with Pipeline Tree-Based Dissemination and Aggregation. In the past few years, there has been an ever-increasing industrial interest concerning permissioned blockchains that support large numbers of validators, such as Facebook DMs or Corda. Most of these solutions rely on BFT consensus, which most commonly are either PBFT derivatives or hot stuff. PBFT uses an all-to-all scheme where the leader broadcasts a block proposal following several rounds of broadcast to collect two subsequent quorums. And in the case of a failure, after a timeout, a reconfiguration, also called view change, is started. The leader is switched until a correct process is found. And as such, within optimal steps, a robust configuration is achieved and consensus can terminate. PBFT has several advantages, including the high resilience, low latency, and optimal reconfiguration steps. However, it suffers from high message complexity. Hotstuff attempts to alleviate this by using a star communication scheme, where the leader broadcasts a block and then aggregates and disseminates the votes of the other processes, such that in the presence of failures, similar to BFT, Hotstuff just switches the leader in a reconfiguration process until the correct process is reached, and consensus can again be achieved within optimal steps. As such, it also offers high resilience, but at a reduced message complexity, still offering configurations in optimal steps. However, at twice the latency cost, since it now needs a round trip instead of a broadcast. Nonetheless, this family of approaches is inherently non-scalable, as one or more processes need to send, receive, and process end messages, which leads to a bandwidth and CPU bottleneck. Due to this reason, alternatives emerged, most notably solutions based on committees and solutions that use dissemination or aggregation trees. Committees are pretty straightforward. Instead of requiring all processes to participate in consensus, a different subset of processes is elected each round. However, there is a certain possibility to eventually reach a committee with a majority of faulty nodes, and consensus will fail, such that these approaches either consider lower resilience or do not provide deterministic safety. A solution that solves all these problems are tree-based approaches, where votes are disseminated and aggregated through a tree. This way, the load is distributed equally among all the internal nodes while maintaining the same resilience as PBFT and hot stuff. However, trees are hard to reconfigure and have a much higher inherent latency than stars, even resulting in low throughput in a geographic distributed setting. In the case of a failure, it is not enough to just switch the leader, as there's a high possibility that even after F attempts, no robust configuration is found, as there's always either a faulty internal or root node. And this is especially complicated as there's a factorial number of trees, where only a small percentage of those are actually robust. In terms of latency, while the message travels through the system, the majority of the nodes are going to stay idle for the majority of the time. As such, the approach suffers from high latency while also having a very poor resource utilization. And that's exactly what Kauri attempts to solve. Kauri is a tree-based approach to address the scalability limitations of the other BFT implementations. It does so by addressing the following main challenges. We want to have optimal reconfiguration for a small number of failures F. We want to compensate the extra latency through pipelining while still maintaining high resilience. Let's start with solving the problem on how to deal with the factorial number of trees and still achieve optimal reconfiguration. We want to construct a tree without any faulty internal nodes to achieve consensus. So we start from a set of nodes where a small subset is faulty. And we divide the nodes into bins of roughly the same size, such that where each bin is at least the size of the number of internal nodes, so 6 or more in this example. As such, if we switch through the bins, assign each bin to the internal node positions, as long as we have more bins than faulty nodes, we are guaranteed to eventually reach a bin without faulty nodes, and as such a robust configuration in F+1 steps, which is optimal. This way, Kauri is able to offer optimal reconfiguration for small numbers of failures, which arguably is the most common case. In the unlikely case of large numbers of failures, Kauri can still fall back to a star topology similar to the other tree-based approaches, maintaining both safety and liveness. Now, the number of failures we can tolerate in the setting is inherently proportional to the fan-out, where the fanout M has to be bigger than the number of failures F. Let's check out some examples. First, let's assume a binary tree with a fanout of 2. As there's a total of 15 processes, of which there are 7 internal ones, this is just enough to construct 2 bins of 7 or more processes. And as such, in this example, we can tolerate at most F equals to 1 failures before falling back to a star. However, for small values of F, if we apply each bin to the internal nodes in the tree, we are still guaranteed to find a robust tree in optimal steps. Now, for the opposite extreme, assume a system with a fanout of 20 and 421 nodes. This results in 20 bins of each 21 processes, which is the number of internal nodes in the system. And for F smaller than M, we can tolerate 19 failures without ever having to fall back to a star. Now, all of these configurations are based on the strict assumption that we require a tree with solely correct internal nodes to achieve consensus, which is potentially stricter than actually necessary. As such, in practice, there's a decent amount of space to relax this assumption, which only aids our proposal. Next, let's talk about the latency, or more specifically, how to compensate the additional tree latency in Kauri to achieve high throughput, even for deep trees with multiple hops. Because instead of producing one block at a time, we leverage the fact that the leader of the system knows the hash of the first block and is able to produce the next block optimistically before knowing the consensus result. And this way it is possible to propose multiple blocks in a row, allowing to fully leverage all the system resources. The only question that is remaining, though, is how many messages can we actually pipeline in the system? To configure the number of messages we can send in parallel, we require some sort of performance model, because for very small values we're going to underutilize the resources, resulting in a much lower throughput than would actually be possible. And for very large values we're going to have a network congestion and a CPU congestion, resulting in a much higher client-side latency. So for that we require a performance model. Considering the total time frame it takes to finish a round, which is mostly made up from the hop latency and the number of hops in the tree, including the computation time at each step, we can calculate a subset from this, which is the idle time, which in a nutshell is the total time subtracting the sending time and the processing time, where the sending time is the time it takes to propagate the blocks, depending mostly on bandwidth, block size, and fan out, and the processing time is the time it takes to compute at the root node, which mostly depends on the fan out as well. This allows us to calculate how many additional blocks we can fit in the idle time. We denote the total number of blocks we can produce concurrently as the pipelining stretch. In a nutshell, the smaller the fan out and the greater the idle time, the bigger the resulting pipelining stretch. Let's look at some examples. First, when decreasing the bandwidth or increasing the block size, this results in double the sending time, which proportionally decreases the idle time and results in a lower pipelining stretch. Similarly, if we increase the fan out, this will lead to an increase of both the sending and the processing time, and inherently again reduce the pipelining stretch even further. However, with increasing round-trip latency or more hops, the total time increases, and the idle time proportionally makes up a bigger share, which also allows to increase the pipelining stretch. Let's look at this from the perspective of the star topology to understand its limitation. A star is, roughly simplified, a special case of a tree with a fanout of n-1. And as such, with this very large fanout, in comparison to our tree approach, in the star the sending and processing time dominates the total time. And as such, there's little to no space to process additional blocks. Let's look at some example values. We configure two types of scenarios. For one's a regional scenario with 100 millisecond latency and 100 Mbits bandwidth, which is like an inner EU or inner US setting. And on the other hand, a geographically distributed scenario we call global with 200 milliseconds latency and 25 Mbits bandwidth, which is like a worldwide geographically distributed blockchain scenario from the literature. And the busy time here is the time we obtained experimentally, which is a combination of the sending time and the processing time. In this first example with 100 millisecond latency and 100 Mbits bandwidth, the system is idle for roughly 230 milliseconds, while sending computing at the root takes no longer than 52 milliseconds. Such that instead of producing just one block, we can put 4 additional blocks inside the idle time, which results in a pipelining stretch of 5, meaning 5 concurrent blocks being processed in the system at a time. If we decrease the fan out, this results in a deeper tree, which increases the idle time and at the same time decreases the busy time, which significantly gives more space for an additional pipelining stretch. However, in the global setting, even though we increase the round-trip latency, which resulted in a much larger idle time, due to the reduced bandwidth we have available, the sending time and with it the busy time increases significantly, which results in a much lower potential stretch. Finally, we did an extensive experimental evaluation in different settings, of which I'll quickly describe you some of the most significant ones. We implemented our prototype on top of hot stuff and implemented support for the additional pipelining, tree-based dissemination and aggregation, and aggregated signatures. We used BLS signatures, which is a type of signatures that allows us to aggregate signatures at each internal node of the system and verify each aggregate and O to one time. We deployed this on Grid 5000, which is a public, large-scale and flexible testbed for experiment-driven research in France, with data centers spread out over different cities. We distributed the processes over the different physical machines so that there were always 20 processes per physical machines, using up to 20 homogeneous physical machines, resulting in up to 400 processes. As we've executed experiments with different latency and bandwidth settings, and there's a high-speed network connecting all the machines, we simulated the network conditions using knitting. This first experiment was executed with 3 different numbers of processes, namely 100, 200, and 400, in a setting of 100 millisecond round-trip time and 100 MB links, which is the regional setting from earlier. Kauri is presented with the 2 blue lines, one with and one without pipelining, and hot stuff is presented in the red line. We configured the pipelining stretch of Kauri according to the previously presented theoretical model, resulting in a stretch between 4 and 6. The performance gap between Kauri in this and hot stuff is very significant in this example, with an increasing advantage at larger scale, which reaches up to 26 times the throughput in this experiment. And due to this inherent scalability hot stuff of the star, even without using pipelining, hot stuff starts performing better above 200 processes and has almost twice this throughput at 400 processes. And the same trend continues in the next experiment. In this experiment, we used a larger latency setting at 200 millisecond round-trip latency and 25 MB links, which is the global setting from earlier. We measured both the throughput and the latency for hot stuff in Kauri, and in order to vary the injected system load, we altered the number of operations in each block, which results in different block sizes. Similar to the previous experiment, Kauri is presented with the blue line and hot stuff with the red line. Again, we configured Kauri according to our theoretical model, with a pipelining stretch between 3 for the very large blocks and 25 for the smallest blocks. First, let me point out 2 oddities in this graph, because at very small block sizes, the very high throughput of our system and the limited number of homogeneous available machines we had oversaturated our system. As such, this data point has a much lower throughput and even suffers a latency penalty than would actually be possible. On the other hand, at large block sizes, we can't fully utilize the system resources, as we can't just pipeline half a block, so that results in loss of throughput. The main takeaway of these results, though, is that due to the bottleneck of the star topology, Kauri not only outperforms hot stuff in all configurations significantly, but also suffers a significantly less dramatic latency increase, which is especially visible if you consider that this is a logarithmic graph. Therefore, Kauri not only displays better throughput, but in many situations when the system starts operating closer to its limits, also in terms of latency. The next experiment shows this in greater detail. For this sake, we maintained a constant block size of 500 KB, 100 millisecond round-trip time, and 100 processes, and just varied the bandwidth. The x-axis displays the bandwidth of the different experiments, and on the y-axis we see the latency. Kauri again is blue, and hot stuff is red, and the same applies to the examples in the rest of the presentation. We see that at some point, with increasing bottleneck at the leader process, both Kauri and hot stuff start displaying a very similar latency, and past this point, Kauri, even though we use a tree with more latency due to the number of hops, Kauri starts displaying a latency advantage in comparison to hot stuff. Next, we look at the trade-offs when increasing the depth of the system. For this sake, we executed the system with 100 nodes, 100 millisecond round-trip latency, and again, varying bandwidth. The plot has the block latency on the x-axis and the throughput on the y-axis. Kauri has with a depth of 2 in dark blue, and the fan out of 10 is at the bottom, and at depth 3 in light blue at the top with a fan out of 5. So, and we can see that this increasing the depth of the tree, which reduces the fan out, will basically double the throughput as what we would expect as well. And actually, interestingly, the additional latency cost is actually relatively little. In the next experiment, we evaluate the impact of failures on the system. So we measured this in the same setting as the global as earlier, with 200 millisecond round-trip latency and 25 MB links. We configure the system in a way such that the current leader fails after 40 seconds, and consecutively, after being elected, the 2 next leaders fail in a similar manner. At this considerably low number of failures, we see that Kauri not only reconfigures in a similar time period as hot stuff, but is also able to scale pipelining back up to the original value to attain similar throughput values as before. Next, let's take a look at this final experiment. Similar to the previous experiment, we have a homogeneous network with 200 millisecond round-trip latency, 25 MB links, and 100 processes. There are a total of 2 scenarios embedded in this experiment. In the first scenario, instead of failing a small number of failures, we failed 33 continuous leaders in a row for both Kauri and hot stuff. There's a number of things we can learn from this. First, we see that Kauri successfully falls back to a star, offering the same throughput as hot stuff afterwards. Second, we see that in the case of 33 faulty consecutive leaders, the recovery time is roughly the same as in hot stuff. In the second scenario, though, we added one additional configuration for Kauri, which is the absolute worst case configuration, where first, for m rounds, enough faulty internal nodes block the consensus progress, and next, the system falls back to a star, and the same faulty internal nodes are then elected as the next 33 faulty consecutive leaders, preventing progress. As expected, in this scenario, we see that there's a small overhead in the worst case due to the additional M reconfigurations. Nonetheless, even in this worst of the worst cases, the system successfully falls back to a star and offers no worse performance than hot stuff. Concluding, Kauri scales to hundreds of processes, outperforming previous work by a factor of up to 28 times without requiring any resilience trade-offs, and still offering optimal reconfiguration for a small number of failures, which arguably is the most common case. We have much more experimental results in the paper, so check that out, and we also have a prototype available on GitHub. Thanks everyone for listening, and I'm happy to answer any questions.